start chapter 2. This is 2.1. I'm going to talk about how we measure change, rates of change. But from this section, there's really only one thing I want to talk about, and then we'll move on. And that is the so-called average rate of change. So given an interval a, b, and a function f, we talk about the average rate of change of that function on this interval. It is given by, here's notation, it's just notation that we use, so we don't know if that's in general. F of b minus f of a over b minus a. Now that might look familiar to you. What is that? This expression here. Yeah?
Slope.
Sure, but we had a name for it before. That's this, yeah?
The difference quotient?
That's called the difference quotient. Okay, so the idea is the following. And yes, it's measuring the slope, but that's kind of what it is. Let's say your function is doing whatever. You can pick a point A, which gives you here, f of a would be the output. Pick another point B, where f of b would be the other output. Now the question is, how do you change on average? On this interval overall, how do you change between these 2 points? And that is measured by the slope, right? This tells you about how much it can tell you how much you increase or decrease on average over this interval. So that's the important word, on average, average rate of change. So for every 1 unit move you move on the x, what is the, on average, how high up you move on the y is the question. So that's kind of like, to go back to that example when we were talking about the different interpretation of slope, and we spoke about the object that was moving at like 40 miles per hour. You can measure over an hour long how far you drove, and you can say, okay, in an hour we covered 40 miles. That means on average we were driving 40 miles an hour. But it doesn't mean that at every point during the trip you were driving at 40 miles an hour. You could have sped up and slowed down, but it all averages out to 40 miles an hour. And you can actually just, ignoring the inside, just say overall on average how much did we change, and that is measured by the slope. And the slope is, again, this is y1 and y2, this is x1 and x2. So you can do the formula y2 minus y1, you get this, over x2 minus x1, you get that. And you end up with the difference quotient. So yes, the difference quotient is the measurement of a slope. Okay? So the above is the form that's most commonly used in this context. So usually when someone asks, if you're asked to find the average rate of change or something, you're normally going to want to use the formula in this way. But it's equivalent to another formula, the other one that we know as the difference quotient. And that's the guy that says f of x plus h minus f of x all over h. The thing is just the point of view is kind of different. Instead of using the x and y values, you're using the distance between the two x values. And that's what we call h. So picture for that one would be, you have your function doing its thing. You call the first value x. You move a distance h away so that this value here is x plus h. And so h is measuring the distance between the two x values. But the same thing applies. This guy now becomes f of x plus h. This guy becomes your f of x. This is your y1. This is your y2. This guy here is your x1. This guy here is your x2. And so if you do y2 minus y1 over x2 minus x1, you actually end up with this one. So it's the same kind of formula. It's just a matter of perspectives. But usually if you're asked a problem like find the average rate of change, what you will be given is the two specific x values. You won't necessarily be given the distance between these x values. You could figure that out. But usually you'll be given two specific x values and a function, and you want to figure it out. So it's most convenient usually to plug into the f of b minus f of a over b minus a form. But it's actually equivalent to this one. It's the same. It's just a matter of how you denote the points. It's where the different comes in. And again, the significance of this number is just how you're changing on average. It tells you, on average, how much your y value is increasing or decreasing as your x value is increasing by a unit. Let's just do an example. Again, for a problem like these, the way I'm going to write this down is pretty much standard. It's not really going to be worded differently in general. So it's more or less what you can expect to see. So first of all, we'll define a function. I think the function was x squared plus 1. Nothing terribly difficult. Yeah, I just decided to do something simple. Let f of x equals x squared plus 1. Find the average rate of change of f of x on the interval 1, 4. By the way, I could rephrase this a little bit. Instead of on 1, 4, you might see the phrase something like from x equals 1 to x equals 4. Right, so I might split those up instead of giving you an interval, or say something similar to from the point where x equals 1 to the point where x equals 4, something similar, but you'll be given the endpoints of the interval somehow. Right, so I'll tell you what my endpoints for my x values are, and we usually consider the a to be the first guy and the b to be the second guy. So it's a very standard route to write for that problem. And I think on the quiz I wrote something similar. Okay, so how do we do this?
You just plug it in.
Plug into the formula, so what is it going to be? So our average rate of change will be equal to, what's the formula?
F parentheses 4.
Give me the general formula first.
Okay, parentheses B minus F A over B minus A.
So especially if you don't have this memorized, which I think at this point you should, but if you want to get to memorizing a formula, you want to copy it down every time you write it down, every time you want to do a problem regarding it. So you'd write that in, and then you plug in the numbers. So your B, you'd read from the question, is 4. You can also get it from here or here. So you know that it's f of 4 minus f of A, which is the first endpoint, the left endpoint, over B minus A. So you just plug in these numbers in. And how do we compute f of 4?
Plug it into the x squared plus 1.
Plug it into here, right? So now we're just replacing the x with 4. So this becomes 4 squared plus 1 minus, now we're going to plug in the 1 squared plus 1, all over 4 minus 1 is 3. That's okay?
Oh,
Yeah.
you have to put the parentheses.
Parentheses, right, when you open a negative sign. Okay, so now this becomes, I can just do the 1 minus the 1 here. 4 squared is 16 minus 1, so that gives us 15 over 3, or 5. So on average, for every time the x unit moves over 1 point, the y value will increase by 5 points. Right? And you can see that at this point where we're at f of 1, our value was 2, whereas once we got to f of 4, our overall value is 17. So we increased from 2 to 17, and we moved over 3 units. So to go from 2 to 17, notice that you increased by 15, but per x unit, there were 3 of them, you've actually jumped by 5 y values per x value. Right? So that's how you can think about that. So we know that what this graph looks like is just the square root of x squared plus 1, but then on 1 to 4, this guy here is at 2, this guy here is at 17, but you can think of it as every time you move over 1 unit, this guy jumps up by 5, so it would on average be at 7. And then you move over another unit and it jumps up by 5, and that will be at like 12, and then by the time you get to the next unit, you jump up by 5 and so on. So that's kind of what's going on. It's telling you how much on average is your y value increasing when your x value is increasing. And it doesn't have to be positive. It could have been negative, but that would have meant your curve is going down. Any questions on this? So basically the average rate of change is thus the slope between the 2 points, but it's nice to use it as this formula. And what's also important is how you would interpret this number. Okay, so it's how the y value changes on average as the x value is changing. Okay. And that's kind of it. The 2.1 is a very small section. I don't even think there are a lot of homework problems on it, but that's kind of all I wanted to do in 2.1. Now we're going to go to 2.2. And the title of this is limits. Now this is kind of a long section. So limits, this is the unsung hero of calculus. So it's a very important thing. It's super important. The difference is, we're going to do it now, we're going to do the topic of limits, and we're going to answer problems about limits, but afterwards, it's like they're not going to matter. We're going to be working on derivatives and integrals and all that stuff. But one thing that is important, and one thing that you'll see very soon, is that even the derivative, the guy that we're going to be working with most of the time, is actually a limit, right? And I'll define that limit for you when we get to it. And the integral is also a limit. So it turns out that the two major things that calculus is about, derivatives and integrals, they're actually limits, right? The basic groundwork that lay the foundation for them is limits. So limits is a super important thing. Without limits, we would not have calculus. That's the plain fact. In fact, if you had to condense calculus into one word, what is calculus the study of, the answer would have to be limits. It would encapsulate everything that calculus is about. If you're given a sentence to describe what calculus is about, then you can say, oh, it's about derivatives and integrals and their applications, right? That would be the sentence long. But if someone forced you for one word, limits would be that word. So it's a very, very important topic. This is where calculus starts, and this is the mathematics that makes calculus a thing to study, as opposed to geometry or some other kind of mathematics. So it's a very, very, very important topic, and it's really a way that we can take a very nuanced idea and make it mathematically concrete in some sense. And that idea is the idea of closeness. Okay? And we're going to talk about how this applies to calculus in general, but right now we just want to focus on the limits. And when we actually start doing derivatives, I'll explain to you a little bit more about the point of a derivative and the point of an integral and how limits can help us in doing those. But for now, we're going to talk about limits. There is a very specific definition for a limit, but it is kind of outside of the scope of this class. Has epsilons and deltas and all sorts of weird symbols in it that we're not going to make use of. So what we do want to make use of is, I'll call this a fuzzy definition. Right? It's kind of just, it's a limit is kind of like this, which is not the usual style we want to do mathematics in, but for this class it's the most beneficial style. It'll also give you a lot of intuition for finding limits. Okay? So, given a function y equals f of x, the limit as x approaches a of f of x, and this is the entire phrase. This is what I say. Oh, the limit as x approaches a of f of x. We might say something like that. A is going to be some number that we care about. Is the y value. Also, the word v is important. It's not always important, but in this case it is important. Is the y value that f of x approaches or gets close to as x approaches a. And that is what a limit is. The notation is the following. We write LIM, below it we write x arrow a, x approaches a, and we write the function beside it. You might put this in parentheses if your function has several terms, parentheses or brackets or something like that. But it's kind of understood. If you have one thing, you write the limit beside it, you can say that. So this is read as the limit as x approaches a of f of x. And if you want to know what is that, it is the y value that we approach when x gets close to the number a. Right? Now, in a more serious mathematics class, the word approaches would be, or close, would be defined more rigorously, right? Because close seems to be a relative term. We're like, what do you mean approach? What do you mean close? Does it have to be like 1 unit away, half a unit away, a quarter unit away? You know, it's a vague term, but it's not something that we have to worry about here. It will be very intuitive in the way that we're going to do it. But yes, math people did figure out a way to say close, and everyone would agree exactly what you mean. But yeah, that's outside of our scope. But that's kind of what a limit is, right? And it's a very simple idea, and it's going to be amazing how this idea kind of unfolds into calculus, but that's what it is. So let's do an example. Let's say we wanted to consider the limit as x approaches 1 of the function x plus 1. Right? So now I want to, first of all, figure out what is going on here by actually drawing the picture. So I have a function y equals x plus 1. How does that look?
1's the asymptote.
Not asymptote, no. X-intercept, the y-intercept, right? And the slope is 1, it's a straight line. Okay, so this is y equals x plus 1. And so now the question is, as x approaches 1, right, so we're going to care about 1 on the x-axis. So when I ask you, what is the limit as x approaches 1 of x plus 1? Meaning, when my x value gets super close to 1, what is my y value getting super close to? Yeah?
2.
2, right? You can literally actually, plug that 1 in and realize that the answer is 2. But I do want to emphasize that it doesn't matter that you're actually at 2. Approach is going to be the right word. But yes, you can figure out that, okay, as I keep plugging in values closer and closer to 1, like 0.9, 0.999, 0.99999, 0.99999, right? As I keep doing that, you'll notice that the output of this function keeps getting closer to 2. It would be like 1.9, 1.999, 1.99999, right? It'll always get closer to 2. As your x value is getting closer to 1, the y value is getting closer to 2. So the answer here would be 2. Because as x gets close to 1, y gets close to 2. And I would want to emphasize, when you're dealing with limits, you really do want to state it in the language in this way. You don't want to say, oh, when x is 1, just plug it in, and y is 2. There are reasons why you don't want to think of it that way, right? Because there are times when you actually don't exist at the point. So for example, I can look at something like this. The limit as x approaches 1 of the function x squared minus 1 over x minus 1. Right? Now let's look at that guy. One thing you'll notice that is this function even defined at 1?
No.
Well, the answer would be no, because you divide it by x minus 1. So I literally can't just plug in 1 as I could have done here. But does that mean the limit exists or it doesn't exist? Or what is the limit?
I think it's not defined at 1, but it exists.
So what do you think we can do here? Give me an example.
Plug in something before 1.
You can plug in something before 1. So you could. So let's talk about strategies, right? Which this is going to tie into something I'm going to say. Yeah.
Isn't it that you have to like factor it out so that you cancel it out so then it does exist at the same time? Or
Okay, well, we'll get to that. So let's talk about strategies. Let's go with this one first because it really, what she said really fits close to the definition. So 1, you could keep plugging in numbers to see, right? So you could go with a table of values. You could keep plugging your x, and you could type your y as x squared minus 1 over x plus 1. And you could keep plugging in values closer and closer to 1. So I could plug in like 0.9, then 0.99, then 0.999, then keep getting closer to 1, which is very elusive. We can't actually plug it in there, right? It's undefined there. And we can even approach 1 from the other direction. We can say 1.01, 1.001, 1. Let's sort of increase that. Right? So we can keep plugging in successive values, getting closer and closer to 1, and closer and closer to 1, and we can try to see what the y value is getting close to. Okay? And this could be a possible answer. That's one strategy. Another strategy would be to do, as he suggested here, and you can think of like factoring, for example, right? You'll notice that you have here an x squared minus 1. That should just scream out at you that's the difference of squares. And you also notice that when you actually factor that, you do get a factor of x minus 1 square, x minus 1 in the denominator. So you could have simplified. So you could have that the limit as x approaches 1 of x squared minus 1 over x minus 1 is, here I can write the limit again. And so I can factor the top, x minus 1 times x plus 1 over x minus 1. Now the important thing is, because we're getting close to 1, we're not actually at 1, this expression is defined for the values of x that we care about. And if it's defined for the value of x that we care about, it's just a fraction, it's just a ratio of numbers. I can actually then simplify this, I can reduce this fraction. And so it turns out the limit of this guy as x approaches 1 happens to be the same as the limit of this guy as x approaches 1. And this is a problem that we've done before. We actually know that the answer here is 2. There's another strategy that might come in handy here. Here's a third strategy. And I'll let you know when to choose which strategy. At the end of the section, I'll probably give you like a little summary blurb about how to approach, because there are many different situations here. But you really have to pay attention to that definition about closeness. So here's a third strategy. We could actually look at the graph. Now you might say, what does the graph look like? Well, we can use the intuition that we got from here. Really, as long as we're not at 1, our function will technically behave like this. So what we'll see here is that it looks like x equals 1, except when you're at 1, there's what we call a hole. That is a technical term, by the way, we'll define later on. Right? So I'm not just drawing a hole, it's actually called a hole, right? Because as long as we're not plugging in 1, this is just a fraction that's defined. And every time I plug in a number, it really reduces to this number. So it really looks like x plus 1 at every single point, except at the point when x equals 1. And at that point, we have a hole. And so now the question is, what would the limit be there? And some of you might say, oh, the limit is not there, but we don't care about the actual y value, right? We care about getting close to the actual y value. What is the y value that we get closest to? Okay? So you'll notice that as your x gets close to 1, super close to 1, but never actually touching it, the y value is actually getting super close to 2. Similarly, from the other direction, which you could have figured out by doing this table, as your x is getting closer and closer and closer and closer to 1, the y value is getting closer and closer and closer to 2. Right? And so at the end of the day, the answer should be 2. Right? So it's very important for you to realize one of the reasons why you want to think of the limit in the language that I prescribed is because it's possible for a limit to exist and have a number and have a value, even if the function itself doesn't have a number and doesn't have a value. So just because a function is not defined doesn't mean that you can't find a limit there. Because the limit doesn't care about being at the point, it cares about approaching the point, getting close to something, and without actually necessarily getting there. So that's a very important idea behind a limit. And what the limit is the y value. So they'll tell you what your x value is doing, and you need to figure out what your y value is doing. Is there a value that my y value is getting close to or not? Let's look at some other examples. And of course, there are some strategies that you can take towards figuring this out. And in certain instances, some strategies are better than others, and we'll talk about those as time goes on. And now I want you to think of another example here. Again, we're going to limit as x approaches 1 of the function f of x. And here I'm not actually going to give you a definition, even though I technically could. Maybe let's just reiterate something that we've done before. Yeah, just for a concrete example, we can redo an example that we did before. Where f of x is a piecewise function. So we've seen piecewise functions before. That's defined as 1 if x is between 0 and 1. And it was defined as x plus 1 for x greater than 1. So this is our function. And you're asked to find what is the limit as x approaches 1 of that function. What do you guys think the answer is?
1.
You think the answer is 1? Okay, let's actually try to figure out. We actually know how to graph this. Let's just graph the picture and see what we're dealing with. Okay, so remind me how to graph this. How do we graph this function? What do we do?
We find out which one is
true, or if both of them are true, like when you put in the numbers.
Okay, so tell me, describe the process. Just tell me what you do first, second, third, what you do. Hmm?
So f of s equals 1, it's just a straight line.
Okay,
So on the interval from 0 to 1, you have closed circles.
okay, so you look at 0 to 1, and for that we're going to graph the function basically y equals 1, right? Which is a straight line, it's a horizontal line, but we only care about that happening in between 0 and 1, right? So here's 1, and so there's a horizontal, really there's a general graph that looks like that, but we kind of don't care about these parts here. And so we plug in the endpoints. If you plug 0 into this, it gives you 1, and you shade it in. You plug in 1 into this function, it also outputs 1, because it's a constant function, it's always 1. So there's our guy. How do we deal with this function? On this interval, we know that we're dealing with y equals x plus 1, and do we know what that looks like? Well, yeah, we actually drew that earlier. So it looks like that. And we only care about the part that's bigger than 1, so we only care about this part, and we kind of ignore that part. Yeah, yeah.
Oh, I was gonna answer, but you already answered it, so.
Oh, you were going to tell me? Okay, yeah. So what was this circle here?
Open. 2.
Close to 2. So when you plug 1 into this function, the result is 2, so 2 is right here. So that guy is, it should be lining up like, so there's a hole here, and then that guy shoots off there. I was gonna come up with just a random picture, but I guess it's nice to remind ourselves how to graph a piecewise function. Okay, so now answer the question, what is the limit as x approaches 1 of this function? One.
It's 1 approaching from negative infinity and 2 approaching from positive infinity.
Well, not approaching from positive infinity necessarily.
Like from the right and left.
Okay, so here's where the definition is important. So the definition said it is the y value that we approach when x approaches something. I told you that the was important, meaning that the answer needs to be unique. You need to think of the limit as some kind of function. The output should just be one thing, right? Now you'll notice that here, if you're approaching 1, the answer kind of depends. It's not always the same number. If you're approaching 1 from the left, right, if you're plugging in numbers approaching 1 from this side, like 0.9, 0.999, 0.9999, 0.9999, the y value is getting close to 1. While on the other hand, if you're over here plugging in values going down, like 0.01, 0.001, 0.0001, 0.0001, turns out you're actually on this side of the graph, and in that case your y value approaches 2. Yeah?
So would the answer be undefined?
The answer is undefined. Exactly. Right? And this is because really knowing the definition is what's going to tell you here. So here, what you can say is, because we need a unique output to say a limit, in this case, this situation does not qualify. Now I know it's tempting to say that the answer is 1 because this is filled in, but you have to remember, the limits don't care about being at the point. They care about getting close to the point. So whether or not these are filled in or not is completely irrelevant, right? So that's the point I wanted to put across. What's completely relevant is what is the unique y value that we get close to when x gets close to something. And in this situation, such a y value does not exist because it depends from what direction you're getting close to it, right? So here, you can say the limit as x approaches 1 of f of x. You can say, the phrase is undefined, but it's much more common to use the phrase does not exist. And people often don't write out that phrase does not exist. They refer to it as d and e. So actually, what is the limit as f of x approaches 1 of this particular function? The answer would be d and e. Does not exist. Why? There's no unique y value. However, it is kind of important to know how the function is behaved. So we do have other kinds of limits that we care about. This leads to the notion of things that we call one-sided limits. Because clearly here, if we only cared about one side at a time, we could get to a number. Okay, so we have what we call one-sided limits. Okay, so these are 1. I'm going to introduce the notation and what it is at the same time. As x approaches a, and you put a little minus sign as the subscript here. This is equal to the limit as x gets close to a from the left. Meaning you're approaching the x value, but you're slightly less than that x value. So that would be from this side. You're getting close to it, coming from the left side, which means this captures the idea of you successively plugging in x values to the left of this function and edging close towards 1. So this guy is called the left-handed limit. Similarly, we say x approaches a from the right of f of x equals the limit as x gets close to a from the right. And that's called the right-handed limit. So this guy here is called the left-handed limit. And this guy here is called the right-handed limit. Let's talk about the existence of a limit. Right? So I told you whether or not the function itself exists or is defined at the point is irrelevant, but here are some things that are relevant. What has to mess up for a limit to not exist? Will come down to the left and right-handed limits. The limit as x approaches a of f of x only exists if the limit from the left exists and the limit from the right exists and they're equal. So for a limit to exist, you can know when one exists from when one doesn't exist by taking one-sided limits. Okay? And this idea is going to be important because if your function is doing something, if your function is doing something, and from the left side you're getting a y value, and from the right side it's giving you the same y value, then overall, when you're getting close, that's going to be the y value. Okay? But if one side is giving you one value, so if this side is giving you one value, and then this side is giving you a completely different y value, these two now, you no longer have a unique y value, and that it breaks. Right? So the limit will not exist. There is no y value that you're getting close to. Okay. So the limit is the y value we get close to when x gets close to something, and it will depend, its existence depends on both sides existing. So now you might ask, Is it possible for each one of these individually to not exist? Might not have asked that, but I'm going to answer that anyway. I'll give you a simple example to convince you of that. Or can someone give me an example where even from one side it wouldn't exist? Note. Because knowing what a limit is one thing, but knowing when you can't find a limit is a whole other ballgame. By the way, I can't even go as far as to say, at points where we can't take limits, we can't actually do calculus there. So it is a matter of supreme importance to know if a limit exists or not. Because if I can't take a limit there, I can't do calculus there.
If you have something that for some reason the domain has to be like all positive numbers, then you can't approach it from anything from the left.
Exactly. So that's a very nice example. It could be the case that it's actually impossible for x to get close to something because that x value is somehow is irrelevant. So example, if you look at y equals the square root of x, that guy only exists for 0 and beyond. So if I ask about something like the limit as x approaches -1 of f of x in this case, right? It's like, what are you talking about? There's nothing to get close to. There's nothing here, right? You can't even, it doesn't make sense to actually even ask that question, okay? Sure, I can ask the limit as I approach 1, but asking the limit as I approach -1 does not make any sense. And even if I go from the left, it does not exist. If I go from the right, it doesn't exist either. Obviously the overall limit doesn't exist, but this is a case where even the one-sided limit doesn't exist. You can't approach that from the left or the right because there's literally nothing there. Right? So it is possible for each of these individually to not even be a thing. But for the overall limit to be a thing, both of these guys need to work and they need to actually work together. I think we'll probably define this in a later section, but I'm going to talk about it now. I don't want to talk about it now. So yeah, notes. For a limit to exist. These are just some takeaways, just summarizing. It's one-sided. Limits must both exist and be equal. Right? And it's possible for both to exist. I gave you an example of when neither of them exists, and I gave an example where the example we had over here of the piecewise function, both limits actually existed, but they gave you a different number. 2. Yeah, limit as x approaches a of f of x. Limit as x approaches a from the left of f of x. Limit as x approaches a from the right of f of x. Do not exist. So that's something you should be aware of. So it is. So pay attention to the definition. Right? It depends on being able to get close to a value on a function. Okay, so if the function doesn't exist, you can't get close. You can't take a limit. And if you get close to two different things, you don't exist. You can't take a limit. Now, sort of a big thing to throw in there at this point in time, but hey, go big or go home. Let's talk about infinite limits and limits at infinity. I'm just going to introduce the idea. We'll do a lot more examples on limits in the next class, maybe the next 2 classes. So we can really get big here, consider some big ideas when it comes to limits. Okay, so now consider the limit as x approaches a of f of x equals L. So this is an equation. So we're assuming that, okay, the limit as x approaches a of this function is this number. So here are the definitions. If L is equal to plus or minus infinity, the above is called an infinite limit. The answer is infinite. What does it mean to get close to infinity? We'll actually talk about that in a little bit. If a is equal to plus or minus infinity, the above is called a limit at infinity. Right? So you're taking the x value to be infinite. So what makes something an infinite limit is the y value. Again, remember, a limit is the y value, right? The y value changes without bound. Right? So if you have a function that as you're moving to the right, it shoots off to infinity, kind of like an exponential function would, that's called an infinite limit. But we can actually take the x value as far as possible into the future, as far as possible into the past, and we can actually look at what a function is doing in that case. So, for an example. Consider y equals e to the x. We know that function looks like this. Now let's talk about the limits that we can talk about with this function. Let's talk about some infinite limits here. Let's say the limit as x approaches infinity of the function e to the x. Meaning, what is my y value doing if my x value is getting super large? As I go far out to the right, just far, far, way out. Just go, no matter how far you've been, keep going, right? If you go super far out to infinity, right? What is the y value doing? Yeah?
That's going to positive.
It's also shooting up to infinity. It's going to positive infinity. So this, in that case, you can write infinity as an answer. Now, it's not actually a number, but for conceptually speaking, it helps us to talk about the behavior of functions. So this is an infinite limit at infinity. It can be both, right? So when the answer is infinite, you call it an infinite limit. If the x or y that you're approaching is infinity, you call it the limit at infinity. What about the limit as x approaches negative infinity of this function?
1 or 0.
Well, look what's happening to the function. What happens as your x goes way off, way out here to negative infinity, right? Like, without bound, it goes that way. Far, far to the left. What's happening to the y value?
It's getting close to 0.
It's getting close to 0. It never actually gets there, but we don't care. That's what the y value is getting close to. Right? So we spoke about the function e to the x before. It's asymptotic to y equals 0, which means it inches and inches closer and closer to 0. It will never actually get there. Quite sad, but that's how we would say. So we can't say e to the e to a huge negative number is 0, that will never be true, but the limit is 0. So the limit can give us an answer even when the function doesn't. It's a very important idea. Lots more to talk about limits. This is just, I'm just throwing a lot of ideas out there, but we'll do a lot more examples next time. I do have a couple things to give back, so we can wait on that.
So we didn't finish the section?
No, we didn't finish the section. This is going to be a long section, but we did finish 2.1.
Okay.
So that's due.